Ultrasonic flow measurement with the transit time difference is based on one simple physical fact. Imagine two canoes crossing a river diagonally on the same line, one in the direction of the flow and the other against it. The canoe moving in the direction of the flow needs considerably less time to reach the other riverbank than the canoe moving against the direction of the flow. If we transfer this concept to the measuring principle, we can see that ultrasonic waves along a diagonal path behave in exactly the same way. A sound wave propagates in the direction of the flow of the medium, such as a liquid or a gas, more quickly than a sound wave propagating against the flow direction of the medium. The difference in the transit time is directly proportional to the flow velocity of the medium. In order to understand the technical background, but without going too deeply into the construction of an ultrasonic flow meter, we can look at the most important features. The transducers, which are always in pairs and mounted under an angle, consist of a transmitting and a receiving transducer, which we can call transducer A and transducer B. The two transducers act both as signal transmitter and signal receiver. The time an acoustic wave needs to travel from transducer A to transducer B, that is in the flow direction of the medium, is known as transit time TAB, and from transducer B to transducer A, that is against the flow direction, TBA. The transit times TBA and TAB are measured continuously. The difference in transit time TBA to TAB is directly proportional to the average flow velocity, Vm, of the medium. Let's see why ultrasonic flow measurement is completely independent of the medium. As we can see in equation 1, the transit time of a signal is the distance between transducer A and transducer B, divided by the velocity which the acoustic signal needs to travel from one transducer to the other. Equations 2 and 3 describe the time the acoustic signal needs from transducer A to transducer B, and from transducer B to transducer A. The transit time of the signal is measured and then used with other variables to calculate the flow. Although the signal travels in a straight line, it is traveling at an angle, alpha, to the pipe axis. Equations 2 and 3 define the flow rate between transducer A upstream and B downstream. The transit time is shorter when the acoustic signal is transmitted downstream, that is in the direction of the flow of the medium, equation 2, than when it is transmitted upstream, that is against the direction of the flow, equation 3. The transit times are measured in rapid succession, tens of times a second. In practice, we can assume that since neither the temperature, nor the pressure, nor the composition of the medium will change in these intervals, that is within milliseconds, they remain constant. So, during the transit time period, the velocity of sound can also be seen as constant. Assuming then that neither temperature, pressure, nor composition of the medium change in such a short time, the resulting flow rate of the medium can be shown as follows. The length of the acoustic path divided by 2 times the cosine of alpha multiplied by the result of dividing the difference between the two transit times by the product of the two transit times. Equations 2 and 3 combined result in the formula path length divided by 2 cos alpha multiplied by the transit time. This represents the average flow velocity. When multiplying the average flow velocity with the cross-section of the pipe, we get the flow rate Q. The cross-section of the pipe is constant for an inline ultrasonic flow meter with a diameter D and transducers, which are welded into the spool piece at a fixed angle alpha. These formulas confirm what we've already seen, that is, that the characteristics of the medium do not affect the measurement. These characteristics include density, temperature, pressure, and the velocity of sound of the medium.